So I'd like today to start talking about 8. Number 8. I mean, we're all developers here, and we all have a special relation with number 8. You know, everything around us is in some ways at number 8. And especially for me, this year, number 8 has been awesome. Every great thing happening in my life has number 8 somewhere on it. So let me share a few of those things here. First of them, 64 bits. You know, 64 bits, 8 bytes. We've managed to ship at Xamarin 64-bit supports on iOS. It was a huge project. Our team worked really hard, and we had a great, great outcome. Next thing, iOS 8. Apple released a humongous app update, 30% increase in the surface. We had to ship together with Unified, with extensions. It was a lot of work, and we managed to pull it out. And another thing is that I'm just about to move. And it's my first house. I'm finally buying it. And guess what? I'm the number of the house. It's 251, which still adds to 8. Yeah. And no, it gets better. Hold on. I'm Brazilian. And in case you guys didn't notice, this year, it was one of the biggest dreams for our nation. We hosted the World Cup. Every Brazilian, no exception, we all love soccer. No, it's not soccer, it's football. Yes, it's football that it's called, the right name of the sport. So we hosted the World Cup. It was a huge celebration, it's a huge party. And guess what happened? We had our team, we had the largest number of goals in a single party in the World Cup history for us. 8 goals in a single party. Can you believe it? The only issue is that most of them went to Germany. We're here to talk, this is a tech conference, so we're here to talk about memory management, which is nothing more than shoveling bytes around. You know, those small buckets of 8 bits each. And a good way to start is to see how memory management works on an iOS. First thing is native, which is ObjectiveC. ObjectiveC uses something called reference counting. Reference counting is very simple to explain. It's that every single object, it has a counter associated with it. It's an int, it's a number, that counts how many other objects are pointing to it. And the Objective-C runtime, when it finds that this number drops to 0, it releases the object. It is pretty much as simple as this. We, on the other hand, we use something called garbage collection. Garbage collection works in a slightly different way. It lets the application run. It will not keep tabs of what's doing. And every now and then, it will stop the application, and we'll check out what's being used, what's not being used, and we'll throw away all the garbage. I guess that's where the name comes from. And because that operation is done in bulk, it will be much, much faster. We really believe that garbage collection is the way to do memory management. So that's what we use. But because the way our bindings are built, every time you're using the Xamarin.iOS APIs, you have objects that actually live in both worlds. They're both managed and they're both native, like string, like NSString or all the UI stuff. Those live in both worlds. And those objects are so special, so interesting to us, that we even given them a special name. We call them the peer objects. And we work very hard on taking care of them. And it's a big part of what we're talking today. Peer objects, they come in 2 flavors. First one are the framework peers. A framework peer is nothing more than a wrap around a native class. Those that come either from the iOS framework itself, UIKit, Foundation, whatever, or those that come from a native binding, if you're using a third-party library. So those are what you would see as the most common types around. And they have a very interesting property. The managed state of a wrapper object, of a framework peer, it can be discarded. Because in fact, there is no state there. If you look at the managed content of a NS string, you're going to find nothing, because all the state, all those small characters you have there, they live in native. So we can discard them if we find that we need to. On the other end, we have user peers. Those are the most important parts of your application, because that's where those are the subclasses of the framework classes. This is your controllers, those are your custom views, and so on. And they hold important state. They actually hold your whole application state is there, or it depends on being there. So we can't discard that, because that's too important, and that's what makes your application what it is. We can't discard that. There's no way around. So there has to be something that glues those two worlds together, that glues the managed world with the native world. And this glue, we call it the binding layer. The binding layer does a lot of things, and some of those are bringing together the two worlds, because we have managed and native, and those two somehow need to talk about. It's kind of like a psychic. You go to a psychic, you ask, let's talk with a ghost, right? And she will work out, so we can talk to the dead world. We, the living, talk to the dead, same way as we, the managed, can talk to the native. And what it does is essentially pick a native object and figure out what's the equivalent on the other side, on the native, and vice versa. The other thing that it does is ensure correct lifetime. That's a key aspect that we all expect to happen, is that if an object is being used, it will stay in memory as long as it's needed, but no more than needed. You don't want objects like the managed object just to go away, even if the native side is there. That would cause a crash. That would cause some weird behavior. That's undesirable, and that's what the binding layer does. And one of the key features for getting that done is something called backing fields. It's not any different than what we have on properties. When you create an automatic property on C#, it gets a backing field, which is this compiler-generated field hidden in your class that holds all the values of your properties. We do the same on our binding layer. For each native property that we expose, we hide there a field that will hold the value, the managed value that we translated from native. We hold that state on those fields. Those are the backing fields, and they are critical to ensure the correct lifetime of our objects. The other thing are weak properties in Objective-C. This is it's a common thing on Objective-C to have weak properties, and that stems from the usage of reference counting. Reference counting is fun, it's interesting, it has all things that a lot of people find amazing, but it has a big downside. It has cycles. So a lot of memory cannot be deallocated automatically. So what they do is they use those things. They can manually do it, or they can use weak properties here and there, which means that pointing to a given object will not make sure that it's kept in memory. The object can go away, your property will suddenly become null. And through all the toolkits, throughout all UIKit, weak properties are very, very commonly found on event handling. So every time you attach an event to one of your views, there is a weak property being set somewhere, a native one. And that's not. And when we were doing when we were designing the product originally, we found that was a very strange behavior. That we could not surface that behavior on our product. You don't want to set an event handler, and that event handler can be garbage collected, can be gone at any time, and you have no control over it. If you subscribe to an event, you just expect that event to be kept there. So what we do is we reify those properties from being weak in Objective-C to be strong in C#, managed. And we have to ensure that this happens. The key thing that makes this possible is something we call native usage tracking. What we do here is essentially keep monitoring the reference count of a specific object. And we can guess by that number if native code is interested in that object or not. And let's say if the reference count is 1, it means that only managed code is taking a look at this object. Because we have to increase the reference count because we're interested in the object. But if the reference count is some crazy numbers, let's say 10, it means that besides managed code, there are 9 native objects looking at that one, pointing to that specific object. So we know that when native code is interested in an object, we must force that object to stay in memory. So we create something that is similar to a static variable. We call them GC handles, which in the end, they are pretty much static variables. So we create those dynamically, and we pretty much force the object to stay in memory as long as native is interested in them. And finally, we have 2 implementations of the binding layer. First is classic, which is what has been around since forever, since the very early days of the product. It's what most applications using the classic mode on monotouch or Xamarin.iOS will use. It's pretty much what all your applications might be using now. Second one is NewRefCount. NewRefCount is something that we've been working on for a very long time. Finally come true. We finally got it to a point where we believe you guys should start using it. And it has a series of advantages. And I guess the best way to see those advantages is to compare them in a key-by-key place. First one would be like with native usage tracking, how they fare against each other. Classic, you only do those native usage tracking for user peers, because those are the ones that have actual state, important state that we need to keep in memory. So we want to keep the managed side, we want to make sure that that thing stays in memory for as long as we have native showing interest. As soon as native is no longer interested and is ignoring that object, the garbage collector can go and collect it, which will give you the expected behavior, which is if nothing is looking at a given object, if it's garbage, it should just go away. On the other hand, and that's the key aspect for relying for correctness. I mean, that and backing fields. Backing fields is what ensure what we call the global correctness, that the whole object graph will stay in memory in a way as you expect. NewRefCount, well, it does for user peers because those have state that is important, but it does native tracking usage for framework peers as soon as they have a weak property set. This means like your UI button, if you attach an event handler to it, as soon as you do that with NewRefCount, we will start tracking the native usage of this object, of that button. And this will ensure that all the weak properties have proper handle, because the object will stay in memory, and will ensure that the manager side will ensure that the object we're pointing to will keep in memory while those 2 are there. And on the other hand, with backing fields, classic mode will have backing fields for all properties, no exception. All properties that we expose through our framework will have a backing field in classic, no matter what it is. Well, probably even if you have like an int field, but if a property holds an object, it will have a backing field. In addition to that, classic needs something that we call implicit roots. Those are the hidden static variables that you can see through the API when you're using static functions from the framework. Like a good example is the UI controller stack. You push and pop them, but by looking at the API, you get the impression that there is like a static variable somewhere hidden that has a stack that controls all those controllers. And well, in fact, with class, there is a static variable, which is a stack in our code. And that's how we ensure something that we call the global correctness. since Classic doesn't track the objects with weak properties, we need to use the backing fields to construct a global graph of the object graph to be completely correct. The managed graph will look just like the native graph of objects. So the garbage collector will be able to drive the whole process there. And this ensures that nothing gets collected before it needs to. NewRefCount only has refcount properties with fields behind them for weak properties. So your views, all views have this subviews property. They are not weak, so they will not get a backing field. Your event handlers, yes, they will have backing fields, but that's pretty much it. No other properties will have. And it doesn't need the backing fields to ensure global correctness. Global correctness comes from native users tracking. And that difference puts the balance, or which one are good, which one are not, like or how they fare each other in more practical terms, in terms of pros and cons. I guess the best way to see how they compare to each other is like it's like being born in a country where there are only unicycles. You're born there. You're 5 years old, your dad gives you your first unicycle, you learn how to use it, you go around, you go every day to school to it, you eventually get good balance, you're there, and it's fine. But then you turn 18 and you decide to go college abroad in this crazy country where there are actually bicycles. Crazy stuff, right? So first time you encounter a bicycle, there's this weird second wheel, which might seem strange. But as you keep practicing, you figure out that it's more stable, it gets you further away, it just feels better. But just because you're just about to experience it after using the other one for a very long time, it will feel uncomfortable in the beginning. And that's how, I think that's the best way to picture how Classic and NewRefCount compare to each other. So Classic, it has very well understood behavior. I think that's the best way, that's the best part of it. We've been doing and using Classic for almost half a decade. So we know exactly where it does well, where it breaks, where there are issues. So we can really work around it and fix it and move on. NewRefCount, on the other hand, have no crashes. The binding layer will ensure correctness no matter what. There will be no more crashes. Well, here got those weird crashes with table views going away too soon. Yeah. Every time you get that crash, don't you see the one like, oh, object selector, object doesn't respond selector, is just going, damn your selectors. Those are gone. No more crashes, just because they're gone with NewRefCount. And the other thing is that NewRefCount has a lot less backing fields, because they're only needed for the weak properties. This means that if you ever looked at how big our objects are, like for our UI kit objects, you will notice that they're pretty big. They're like hundreds of bytes because they have tons of backing fields. But with NewRefCount, the majority of those are gone. Objects go from 200-300 bytes to maybe 20 to 30, which is which translates in big savings. And on the other hand, the cons where they really suck is that with Classic, well, there's broken lifetime tracking. And that comes from the fact of relying on backing fields for correctness. This means that unless there's always a backing field that exposes a relationship between two native objects, if there is no backing field for that scenario, we're going to crash, we're going to break, because it relies on having a backing field all the time, mimicking the native graph on the manage. If that goes away, if that's not there, it will crash. So it's a big deal. We worked hard to avoid that over the years, but there are cases where the native API just doesn't expose those things, so we can't just go and poke inside the implementation from Apple. We need to rely on the public API. So there are some crashes that there are no way around it. And NewRefCount, because it uses native tracking to ensure correctness, it means that it will force more objects to stay in memory, and that will cause more cycles. Those cycles are sometimes annoying. Sometimes they're very distracting to figure out where they are, how to fix it. Well, fixing is actually sometimes easier. You just dispose stuff, you unlink stuff, null out stuff, and that's it. But finding them can sometimes be trickier. So it is a problem that we pondered with for a long time. We're really concerned if the fact that there were going to be a huge amount of, lot less crashes, if that was worth having more cycles. We are not this. We threw out dozens of prototypes of systems that are 10 times crazier than this because we thought we could get rid of both problems, and it turns out it's a very researchy problem. So that's why our boss let us go get to 12. Other thing, Classic has unexpected memory retention. And that comes from the very fact that it uses a lot of backing fields. For the same reason that sometimes the native framework doesn't expose a backing field for an object relation, it can go the other way around. You can have the backing field, but there is a function that for some reason changes the object graph. And if we don't find this out and refresh the backing field to have the new information, it will be stale, which means that it could be holding back in memory objects that should be collected. We had tons of problems over the years. We fixed all of them, but they will keep popping up because it's a fundamental problem of that approach. So we'll keep patching up. We got really good at building tools and tests around it, but it will keep happening. And finally, I'd like to say that NewRefCount is perfect. It fixes all the problems, but we got a long QA cycle. We did a lot of testing. We make sure that it works. We could not find any crashers, but then there's this thing called reality. All vendors will say, "Wow, it is awesome. It will work," but then no one is perfect. We're not going to get it right, at least not all the time. So it's a new feature. It is no longer experimental, but it has not been that battle tested as Classic. Classic has been used for almost 5 years, so it has a lot more exposure. It's not like so it has a bigger likelihood of having bugs. And Classic, another thing that is problematic there that I already mentioned is the fact that it does increase the memory consumption. And despite the fact that devices have more and more memory, I don't know, most high-end devices have gigs of memory, we still have to realize that some markets will still have the majority of old phones, even on the Apple ecosystem. And people expect to be able to run more and more apps. Phones are getting more and more close to what the desktop used to be. But the difference is that if your app is using too much memory and is on the background, iOS will just kill it. And it will pick the bit, and it will just pick, iOS goes like this. It needs more memory for the foreground application. It will just look there and try to find the fat piggy. Oh, that one. If you're using more memory than other applications, you have a higher chance to be killed. So you should always have an edge against the other applications because you're, in the end, competing for background space. And being able to use less will make a difference. So a good example, this is a good example of where Classic fails. This has been documented for a long time, and we found this out for a long time. And there are lots of workarounds, but it's something that, we know it fails, and here's where. What we're doing here is we're creating a table source. So on iOS, you create your table, and you create this table source that will feed the cells that will be displayed in your table. And that's what we're doing here. We're creating a new cell. We're adding a text field to it. we're setting an event handler, and we're returning the cell so the table can display it. The thing is, we're not setting a property. We're not doing anything. We're giving back that cell to UIKit, and they will put it somewhere. So we have no control where that is going, which means that we have no backing field between the table and the cell. And this void in the middle will cause Classic to misbehave. And this works with NewRefCount exactly because the event handler is a weak property. So as soon as we attach the event handler to the text field, it will start to get native tracking. And that will ensure that it stays in memory as long as this cell is being displayed, as long as this cell is not disposed, as long as it's not garbage collected. And this is an example where NewRefCount will get you more cycles. Cycles in NewRefCount are slightly harder to see than on Classic. Not that they're easy anyway, but the way it goes is we're creating a view, we're adding a button to that view, and we're setting up an event handler here for this view. The problem here is that the delegate itself, the event handler that is actually, the event handler is capturing the parent of the button. You can see that it is making sure it is there. You see view.remove from superview. That's capturing. So it means that as long as the delegate stays alive, the view will not be collected. And that view is what bumps the reference count of the button from 1 to 2, which means that native tracking will keep that object in memory, creating the cycle. In that case, it's very easy. You just need to either dispose the view, you need to remove the button, you need to unsubscribe the event. There are many options, and that will get rid of the cycle. It's something that if you have a very good hygiene with disposing your views after you're done with them, this will not be such a problem. And yeah, I explained the advantages and disadvantages, but that gets to the point. So okay, wow, great. So which one should I use? So get your app, see how it works, and if you're suffering from crashes because things just go away and you're not expecting it, if things are just failing and you cannot really understand why, if you're suffering from unexpected memory retention, things that you are 100% sure should be collected, and for some reason they just stay around. And finally, if you have good practice with disposing your objects and you're not afraid of fighting more cycles, then NewRefCount might be for you. It is a great development by us, and we would be really happy to see you guys starting to use it and give us feedback on whether it improves your application or not, or if, let's say, if the cycles are too bad, the cycles problem is too bad, or if it's not a problem at all. And the binding layer, it fundamentally deals a lot with the garbage collector. And it's very good to know what's happening with the garbage collector. You should understand how it works, why it does what it does, and see if that is a problem for your application or not. And the best way to see it, at least today, is to enable GC logging. That will print you a lot of output every time the garbage collector does something, like every time the garbage collector runs, and that's your main point of contact. You don't really care if it's doing something in the background that you cannot see, but you care when it runs and it actually impacts your application, because it will tell you how much memory it's using, how much time it's taking. So to get GC logging, oh, sorry, where is it? Oh, so the first thing we have to realize is that we need to switch to SGen. Who's here have ever visited Boston? OK. If you've been to Boston, you have taken the Green Line, because it goes straight through town. The Green Line is the oldest subway in the US. It's more than 100-year-old. And the cars are pretty much the original ones. It is bad. I mean, it gets extremely hot in the summer. It gets not so hot in the winter. It's crowded. They're slow. They're noisy. It is a pain. But it got us through all those years. It has been a great thing for Boston, regardless. But it's time to replace it. We have new lines, new subway lines in Boston. They're awesome. So, and this is pretty much the same situation we have on iOS. We have Boehm, which is a garbage collector that is from the late 80s. And we have SGen, which we have been developing for over 7 years now. SGen is a much more modern. It is based on very bleeding edge technology. It's a generational garbage collector. It can compact memory. It can do things that Boehm was never designed to it. So it's really important that for you to get better results replication, you switch to SGen. SGen is going to be the default with Unified, but it's still not there with Classic in terms of the API. So now, first thing is NewRefCount. It was designed with SGen in mind. The whole thing was always meant to be used. They were meant to be used together. Eventually, we got Boehm support, but SGen and NewRefCount, they really go well together. They're much better integrated. The other thing, SGen has a much superior performance. Because it's a generational garbage collector, it means that it can deal with a lot more churn than Boehm. It also means it can defragment memory. So your application will not have an unbounded, the memory user will not explode under you. And the other thing is, at our platform engineering division, we now have a performance team, and they only work on SGen. They're not doing performance work on Boehm. So if SGen is fast today compared to Boehm, it will get much faster in the future. All the feature work for our garbage collector, all our focus is going on SGen. We want to make sure it is the best garbage collector around. And we want to make sure Boehm doesn't break. That's like our fail-safe garbage collector. But it should not be there. We want to eventually deprecate and remove it and focus only on SGen and gain from having a single one. Besides that, right now, it's the only garbage collector that has support on the profiler. If you're using the profiler to do memory profiling, memory instrumentation, it will only work with SGen. And since you're profiling with SGen and figuring out how your application behavior with it, it doesn't make sense to use Boehm on your final app because they will not behave the same. So if you profile with SGen, you ship with SGen. And if memory profiling is something you're looking for, then you probably should use SGen. And now to enable GC logging, which will let us see what's going on, you just go to your project settings and run, and you add those two environment variables. The first one, mono log level debug, and the other one is mono log mask GC. We have some really good docs on that. If you want to see that later, but it's pretty straightforward. And as soon as you enable and you run your application, you go to the console, you're going to get a bunch of lines like this. This is the GC logging output from SGen. I'm not going to cover Boehm because I hope I have sold out you guys on using SGen. So it's going to spawn you a lot of those lines, those very cryptic, full of weird numbers lines. So let's figure out what's going on there. First thing, the kind of collection. SGen is a generational collector, so it does minor collections or major collections. Minor collections just collect a very small part of the heap that is very fast to do it, so it's going to be it's going to be much more frequent, but it's going to be super fast. Major collections are when SGen has to collect the whole heap, so it's going to be slower. Then it's something you need to pay attention. If your rate of minor collections and major collections, what the rate between those. If you have one major collection for each minor collection, then something is wrong there. If you're getting like 10 or 16 minor collections before you have a major collection, they're doing super well. So next, we have the reason why the collector run. First one, which is nursery full. That's when you allocated all memory available for the nursery. Nursery is where all baby objects are born. Yes. And as soon as they grow up, passes some time, we send them to the major heap. And we'll end up with nursery empty, and we'll allocate that all over again. The second one, which is user request, that's when some line in your code called gc.collect was an explicitly triggered garbage collection. There are reasons to explicitly call the garbage collector. It's not trivial to know when to do it or where to do it. So if you see a lot of those user requests, you should really pay attention because they could really degrade the performance of your application, especially because it will introduce a lot of jitter in there because it's a slow process. Here we have the pause times. As you can see, a minor collection is significantly faster, half a millisecond compared to the other one where it's 6 milliseconds. This is from a benchmark on a desktop machine, so those are not the kind of numbers you get on mobile. They will be higher, but they're going to be on that order, where the minor collection is significantly faster. And this is pause time, so it means that your application is not going to do anything else while the collector is running. It's like your application is holding its breath for 6 milliseconds. So in the same way, if your application holds its breath for hundreds of milliseconds, it's going to look ugly. Don't try that. Next thing, the amount of objects that got promoted. As I told you, as soon as when we run a minor collection, we get those baby objects, and we move them to the major heap. And this tells you what the natural flow, natural cadence of major collections are going. As soon as the major heap is full, or it has enough objects promoted to it, we run the major collector. And so you should watch out for having a low promotion rate. The default nursery is 4 megabytes. So here you're promoting very, very, very little objects. That's like the sweet spot for SGen. Very low promotion rate. Now we have the size of the old generation. We have major and loss. Loss stands for large object space. And it's where the big objects go. We don't create the big objects in the nursery. If you create something that is over 8,000 bytes, it will go straight to the large object space. It's a very important distinction between large object and major heap. The major heap is where the small objects go, and the large object only when the big ones go. And since the large objects don't go through the nursery, it means that they will pile up faster. So if you're producing too many big objects, you're going to trigger major collections much more frequently, and that's a problem for your application. Okay, here you can see that we're using something like almost 6 megs of memory. Next, we have the memory usage on the major collection. I think this was done when I was still living in Brazil, so it's flipped. You're not expecting to get first the after number, then the before number. So here we see that we run the garbage collector. At the beginning, we have 5 megs, some 5.7 megs of memory used by the major heap. And when the collector ended, it has the same thing. It is a very good example of a user-triggered garbage collection that went really, really wrong. So you asked the garbage collection, run for me. And what it did nothing. It spent 6 milliseconds where your application could not interact with your user, and it got no more memory for you. So this is a good example where user explicitly triggering the garbage collector. It's a good example where it went really, really, really wrong. It's the console, so we cannot put like an epic fail image, but you get the idea. Sometimes just the GC login is not enough to understand what's going on. So what you might want to do is to throw out your application to get memory usage numbers. So you can report to, I don't know, Xamarin Insights or send to your own server for tracking usage, or just print to the console, or put a magic number on the corner of your app. Few interesting tricks here. First one, gc.getTotalMemory. This puppy will go over the heap and sum up all the usage memory for your application. You'll see, well, you have like 20 objects, 10 bytes each, 300 bytes. It's not a slow, it's a slow call, but it will get you an idea of how much memory actively you're using. Next one, mono gc get heap size. This one is part of the C API for the runtime, so you're going to get your hands dirty with pinvoke. It's not the end of the world. We all have been there. It's going to be fine. This one here, it returns the total. It returns an estimate of the total usage of the GC. It's not just your objects, because the GC holds your objects that you're using, plus some free space that is going to use for the objects you're about to allocate, and plus some overhead. You know, like I don't know, like management in some ways. And this one will return you that number. This one is what, if you're using some native tools to track memory usage, you can better correlate the total memory usage of your application with your GC memory. This one will get you a better number. So let's say you fire an instrument and say, wow, instruments tells my application's using 100 megs memory in total. This one here you're only using 20 megs of GC memory. So there's this extra 20 megs that's going, 80 megs that's going somewhere else. There's one small gotcha. Because this is a very low-level function, it reports on very low level. And SGen does some really crazy stuff in there. It will report 8 extra megs of memory for an SGen. So for an empty heap, it will report 8 megs on start. So take that into account, and don't freak out because you have like a hello world using 8 megs of memory, which is kind of insane. Don't worry about that. Finally, we have XamCore get surfaced objects. That's a call we're not supposed to mention because it's only used during support. So don't tell my boss. This will return you all the peer objects that are currently alive. It is great for you to figure out like what's being kept in memory, what's not kept in memory. So to figure out if you're about to crash because some of your cells are missing, or if you're finding, like, say, if you figure out the memory usage is high, and then you figure out, oh, but all my controllers are still kept in memory, and then you can go search where those are. It's on its own, it doesn't give you any information, but it's good to start digging where things are going. We've been using that for many, many years, and it has been very, very, very successful as a way to figure out memory usage problems. That's how, for example, all the extra memory retention problems we had, that's how we diagnosed those. And one last thing, this is a word of advice, calling GC collect explicitly and triggering the collection, there are use cases for that. Like you want to improve the responsiveness of your application. But you have to be extremely careful where you put those calls because you're actively increasing the amount of jitter your application, pauses your application is getting. So if you're going to do it, you have to hide it in a place where the user is not going to see. Let's say if you're playing a YouTube video, so while your user is enjoying Nyan Cat, you can put a GC collect there. And besides that, there's our new awesome profiler. There's going to be a talk on the profiler across this hall right after now. Really, 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 really suggest you guys go there. It is an amazing tool. We're finally relieved to be able to talk about it and, most importantly, release it. The profiler has 2 very important things for memory management. It can report to you allocation sites. So when we're figuring out where all the fat cats in your application are, where this huge 1 meg array comes from, the profiler will tell you the exact stack trace from there. It's perfect. It helps a lot. It's how we, for example, optimize mono all the way through the years. We use tools that would report those things. So we know how great this kind of tool is, and we're so happy to be able to get you guys that. The other one is that it can take memory snapshots. Snapshots, it's kind of what the name implies. It takes a picture of your objects, or take many of them. It allows you to compare them. So you can, for example, say, I'll take a snapshot right before displaying this controller here, and I'll take a snapshot right after. And that will give you an idea how much memory bringing that controller in costs, how much memory you're bringing in. And it's interesting to do even on the other end. Let's say you have your very expensive view, and you want to know if you're doing everything correctly to clear memory after it goes out. So you show your view, you have all thousands of widgets showing, you take a snapshot. You're going to say, well, yeah, it's using a lot of memory. So you click back, You go to something else, and you take another snapshot. OK, now it's using as little as you were expecting. That's, there are a lot of practices. Right now, the profiler contains a lot of we're still building up the tools. But there are a lot of practices and techniques that we're going to, over time, document and display and offer to how to better use the tool. OK, so today, we talked about two things in this part, here. We talked about NewRefCount, which is what we think is a much saner thing. You're going to be pulling a lot less hair because your application's crashing. So the gain you get there will more than offset your problem, the additional problems. We think it's a much better solution. The other thing is SGen. We talked a little bit about the advantages. We saw how the logging works. And I think it's really the way to move forward. You should be using SGen now because that's where all our energy and all our love is going to. And with that, thank you. I'll be getting questions now. Any questions? She'll be taking the questions for me. Thank you, Aisha.
I have a few questions. One is how many generations you have in SGen. Basically, I only heard about 2, nursery and the large heap objects. And the second one is, with the new reference counting, is closure still a problem or not? Closure and abstract method, something like that. Thank you.
So the first question is, how many generations SGen has? OK, SGen has 2 generations. It's pretty much what everyone does. Some say they have more, but in fact, what they have is they have a more complex organization inside their own generations. Like that's what Java does. That's in some way what .NET does. So we use this very standard setup. We have a nursery, which is fast, and we have the old generation, which is slow. The only thing is that on the old generation, we use a more fancy organization that is meant to minimize the memory usage. And the other question is if with NewRefCount, there's still problems with closures?
Yes.
So the difference is closures will, in NewRefCount, they might introduce more cycles, but they will not get a problem of being collected. So you're not going to get more crashes. They're not going to go away and crash, which was what used to happen before.
First, I do want to say, like, I've seen the improvements in SGen performance over time, so I definitely appreciate those. Sometimes in your app, you have times that are really, really bad to have any sort of garbage collection at all, including nursery collections. And .NET and on Windows has stuff where you can basically tell the system, please do everything you can to not run the garbage collector right now. Do you think you'll ever have support for that kind of thing?
OK, so the question is if we have a low latency mode for SGen. We have an experimental thing that we're working on. We have basically what you need to get low latency is that you need a concurrent collector. And when you want to sustain low latency, you want to try to use the concurrent collector as much as possible. So you're going to assume that you're OK with getting more fragmentation. So that's, for example, how most of those sustained low latency garbage collector works. They say we're going to use probably twice as much memory, and we might go get an out-of-memory exception instead of running a very slow collection. So you have to pay attention to that. And the other part is having a concurrent collector that will do the majority of the work without stopping your application. We already have a concurrent collector. It's not ready yet to even be called an experimental feature. We have it internally. You can see it on GitHub or it's an open source project, Mono, so you can see the code there. Because it's very experimental and because we don't believe it's ready for to show it as a preview, we don't ship that on iOS or Android. We think, well, not actually shipping 200, like putting 300K less in your application size for something that you're never going to use at this current stage made more sense for us. So we don't ship it now. You can try it on the desktop, but that will not make your customers happy, I assume. OK? All right, one more.
Can you hear me? Why isn't SGen the default on Classic when it is on the new?
Because iOS 7. iOS 7 introduced some really crazy changes. And for the first time, SGen broke on an upgrade. So we were back then, that's last year, we're ready to switch, to make the switch. We say, well, it's going to happen this year, we are super happy. Then iOS 7 happened, and we broke it. So we got a little bit scared about making the default. And so we fixed that. We fixed that almost like a year and a half ago almost. But ever since, we haven't got any other reports of crashes, or they're very, very, very few. We got as many as Bowen at this point. So we haven't evaluated making the default for new apps. We really want to make it. If we haven't done yet, it's mostly because we have been busy with everything else. We'd like to make it a default. We'll be doing that at some point. But right now, it's what you get on. It's the default on Classic. On Unified API. On Classic, we'll get there. But what we're not going to do is switch it under the hood. You're not just going to open your project, update on stable channel, and get SGen without knowing it. So existing projects will stay we're using the garbage collector they picked today. New projects will eventually get to the point where SGen is a default. It's the same thing for NewRefCount. We eventually want to make sure, as soon as we get enough testing, enough feedback, and we feel confident enough, we'll make it a default for new projects. OK, any more questions? OK.
To continue the question,
right.
what kind of thing actually making you actually kind of want to delay a bit on making it as a default? I mean, a technical limitation or something more like psychological things?
You mean on NewRefCount?
No, on SGen.
It was just a bug that broke the whole thing. So we got kind of scared. Because we, so for us, so since we were on the runtime team, we're very scared of big changes. Like sometimes it will take many, many months to roll out huge changes. And we usually like to keep them always as optional. We never roll out big changes as default. So we like to do very gradual changes. And we had this big scare on iOS 7, and that's what made us take a longer time. If it wasn't for that, we would probably be the default by now. That was the last question. If you guys have any other questions, just find me on the corridor. Thank you so much.